Welcome to the deep dive. Today, we're diving headfirst into something so fundamental, so ubiquitous, you probably interact with it dozens of times before breakfast, the world of measurement.
It's everywhere, isn't it?
Absolutely. Whether you're measuring ingredients for a recipe, figuring out how far your morning run was, or even, estimating how long this deep dive will last, understanding measurements is absolutely crucial. And for today's exploration, we've compiled a fascinating stack of sources focusing on those foundational grade 5 measurement concepts. Our mission isn't just to recite facts, but to equip you, our curious listener, with a deep understanding of these core ideas and then walk through how to apply them to real-world challenges, turning seemingly simple numbers into, well, powerful insights.
It's remarkable, isn't it? These concepts, often introduced pretty early in our education, they form the bedrock of so much advanced thinking. From the precise calculations behind, say, space exploration, to the everyday task of laying out a new garden bed, it all comes back to understanding units, their relationships, and how to use them effectively. We're essentially giving you a shortcut to thinking like an engineer or maybe a chef just by re-examining these basics.
Okay, let's unpack this then. First, big idea, length and distance. When we talk about how long something is or how far away, what are the primary systems and units we absolutely need in our toolkit?
Well, we primarily navigate the world of length and distance using two major systems, the metric system and the imperial system. In the metric system, we have the millimeter, centimeter, centimeter, meter, 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 and kilometer, kilometer. What's kind of elegant about metric is its inherent logic. It's entirely based on powers of 10. This makes conversions incredibly straightforward. You're either multiplying or dividing by 10, 100, or 1,000. It's why it's the global standard for science and commerce, reduces ambiguity, and simplifies cross-cultural communication.
And then there's the imperial system, which, well, many of us in certain parts of the world grew up with.
Precisely. On the imperial side, we encounter the inch, in, foot, eft, yard, and the mile, mi. These units often have a more organic, sort of human-centric origin. Think of a foot literally as the length of a human foot, or an inch maybe related to the width of a thumb.
Makes them feel more intuitive sometimes.
Yeah, almost tangible. However, this natural evolution also means their conversion factors aren't as uniformly decimal-based. They can be a bit trickier to remember and manipulate.
Okay, so let's talk about those essential conversion facts that our sources highlight. Give us a couple of those crucial connections between these units, the ones that really unlock their utility.
Absolutely. Here's where we start connecting the dots. In the metric system, you have 1 centimeter equal to 10 millimeters. You can see that on any school ruler, right?
Right.
Then 1 meter gives you 100 centimeters, which is the span of a meter stick, a common reference. For longer distances, 1 kilometer is a significant jump at the 1,000 meters, which we use for travel. The beauty here is the consistent power of 10 relationship.
Nice and clean.
Yeah. On the imperial side, it gets a bit more varied. 1 foot equals 12 inches, a standard we use for height or smaller measurements. Then 1 yard is 3 feet, often applied to fabrics or sports fields.
Okay.
And a mile, that's a whopping 5,280 feet.
Wow, yeah.
The insight here is that while the numbers differ, the principle of conversion, multiplication, or addition remains constant once you know those factors. Understanding these conversions isn't just about memorization, it's about translating scale, whether you're building a bookshelf or, planning a road trip.
That breakdown of metric consistency is truly elegant. And speaking of elegance, it's not just about one dimension. Our sources really dig into how we quantify space in 2 dimensions with area and perimeter, which, they're often confused. How do we distinguish them effectively, and why does that distinction matter?
Oh yeah, this is a classic point of confusion, but the distinction is critical and has real-world consequences. Perimeter is simply the distance around the outside of a 2-dimensional shape. Imagine walking around the edge of a room. The total distance you walk is the perimeter.
Okay, the edge.
Right. It's a linear measurement, typically in units like feet or meters. Area, on the other hand, is the amount of surface space inside a shape.
The space inside.
Exactly. If you're carpeting that same room, you're calculating its area, and that's always measured in square units like square feet or square meters.
Ah, square units, that's key.
It is. Confusing them can lead to buying way too much paint or, not enough fencing.
And our sources give us some pretty straightforward formulas for common shapes, like rectangles and squares, making these calculations accessible.
Indeed. For a rectangle, if you're looking for the perimeter, you're essentially adding up all 4 sides. The formula simplifies to 2 times the sum of the length and the width. So perimeter equals 2 length plus width.
Okay.
For its area, you simply multiply its length by its width. area equals length x width.
Simple enough.
Now, a square is mathematically just a special, highly symmetrical kind of rectangle where all sides are equal.
Right.
So its perimeter simplifies to 4 times the length of one side, or quantify complex spaces with just simple measurements.
Now let's add another dimension. Moving into 3 dimensions, we've got volume and capacity. These often get confused too. So what's the core difference and why is this distinction important, especially in like practical applications?
Yeah, this is a really important distinction, especially in fields like engineering, chemistry, or even cooking. Volume is the amount of space a three-dimensional object takes up or occupies. Think of a solid block of wood. Its volume is the space it displaces, whether it's solid, liquid, or gas.
Okay, the space it takes up.
Right. Capacity, however, is specific to containers and refers to the maximum volume of fluid, liquid, or gas they can hold.
Ah, what it can hold.
Exactly. So a solid block has volume, but no capacity.
Huh.
A bottle, conversely, has its own volume as an object, but also a distinct capacity for the liquid it contains. They're intrinsically linked, of course, as a container's internal volume determines its capacity.
And again, different units are at play here across our 2 measurement systems, right? Metric and imperial.
Yes, exactly. For metric, we commonly use milliliter, ml, and liter L. These are, well, ubiquitous in cooking, medicine, and science. Think of a 2-liter soda bottle, maybe a 5 milliliter dose of medication.
Yeah.
In the imperial system, often seen in the U.S., we have cups, pints, quarts, and gallons. You'll encounter these frequently in recipes, for example, when a recipe calls for 2 cups of flour, or when buying milk by the gallon.
Okay, so those conversions.
Relationship again.
1,000. Got it.
For imperial, it's a bit more of that nested doll structure we saw with length. 1 gallon equals 4 quarts, 1 quart is 2 pints, and 1 pint is 2 cups.
Ah, okay, so you need to remember those steps.
You do. Understanding this hierarchy is key to making sense of things like a half gallon of ice cream or a pint of beer.
And for objects that aren't holding liquid, like a box, how do we find their volume?
For a simple three-dimensional shape like a rectangular prism, essentially a box, it's quite straightforward. You just multiply its 3 dimensions, length with x height.
Length times width times height.
Yep. This gives you the volume in cubic units, like cubic centimeters or cubic feet. This is the first step in calculating, for instance, how much sand you'd need to fill a sandbox.
Right, okay. Let's shift gears now to how heavy things are. We're talking about mass and weight. And while we often use these terms interchangeably in everyday conversation, there's a crucial distinction, isn't there?
Absolutely.
Wow.
While we might say we weigh a certain number of kilograms or pounds, conceptually, mass and weight are different. Mass is a fundamental measure of the amount of matter in an object. It's a constant regardless of location. Your mass would be the same on Earth, the moon, or, in a deep space.
Right, same amount of stuff.
Exactly. Weight, however, is the force exerted on an object due to gravity. So your weight would be significantly less on the moon because of its weaker gravitational pull, even though your mass hasn't changed one bit.
That makes sense.
For grade 5, we often kind of conflate them, but understanding the underlying difference is a powerful insight later on.
And the units. Metric and imperial again.
Yes, as expected. In metric, we use gram, g, and kilogram, kilogram. Again, the beautiful simplicity of metric shines through. 1 kilogram is exactly 1,000 grams. This system is universally used in science and is ideal for everything from precise chemical measurements to, well, determining your body mass. For the imperial system, we use ounce, ounce, and pound, pound-el. You'll see these in grocery stores, buying produce by the pound, or maybe measuring baking ingredients in ounces.
And what are the key conversions for mass and weight that our sources emphasize? The need-to-know ones.
The essential conversions here are pretty simple. 1 kilogram equals 1,000 grams.
Okay, 1,000, yep.
Yep. And 1 pound equals 16 ounces.
16, okay.
These are simple ratios, but mastering them is crucial for everything from following a recipe accurately to understanding shipping weights. The insight here is how these systems provide different scales for measuring the same underlying property, the quantity of matter.
Finally, a measurement we're all acutely aware of, and perhaps the most universally understood, time.
Time. Yes, the great equalizer, moving relentlessly forward. Our basic units are the second, minute, hour, day, and week.
The classic.
The classics. The conversions for these are deeply ingrained in our daily lives. 1 minute equals 60 seconds, 1 hour equals 60 minutes, 1 day equals 24 hours, and 1 week equals 7 days.
Pretty standard stuff.
It seems simple, but the real challenge And a critical everyday skill comes with calculating elapsed time, finding the duration between two specific points in time.
Right, how long did something take?
Exactly. It's how we figure out how long a flight will be or how much time we have before an appointment. It's a constant mental calculation we're doing.
All right, we've solidified our understanding of these core concepts and their essential units. We've got the theory down, now let's put them to work. Our sources provide some excellent practice problems, and we're going to walk through a few, not just to get the right answer, but really to illuminate the strategy and the thought process behind solving them. Think of this as your practical training, kind of a shortcut to confident problem solving.
Exactly. It's one thing to know the definitions, it's another to apply them effectively when you're faced with a real situation, or even just a word problem. This section is all about translating those theoretical concepts into actionable steps, focusing on unit analysis and formula selection. Let's dive into some examples.
Okay, let's start with a length and distance word problem. Problem 1. Sarah's bedroom is 3.5 meters long. How many centimeters is that?
Okay, let's unpack this problem methodically. We need to convert meters to centimeters. First step is recalling our conversion factor. We know that 1 meter is equal to 100 centimeters.
Right, 1 meter is 100 centimeters.
Since we're going from a larger unit, meters, to a smaller unit,
Yes.
centimeters, we expect the number to get bigger, so we'll multiply.
Multiplier.
So we
Yeah.
take Sarah's bedroom length of 3.5 meters and multiply it by 100. That gives us 350 centimeters. The insight here is knowing whether to multiply or divide based on the direction of your conversion. Larger to smaller means more units, multiply.
Straightforward enough. Next up, an area and perimeter challenge. Problem 3. Maria wants to put a fence around her rectangular garden that is 12 feet long and 8 feet wide. How much fencing does she need?
Okay, this problem provides a perfect opportunity to differentiate between area and perimeter again. The key word here is around.
Around, yeah, that usually means perimeter.
Exactly. It immediately signals that we're looking for the perimeter of the garden. For a rectangle, our formula is 2 times the sum of the length and the width. So we plug in Maria's garden dimensions, 2 multiplied by 12 feet plus 8 feet.
Okay.
First, we calculate the sum inside the parentheses. 12 plus 8 equals 20 feet.
Right.
Then we multiply that sum by 2.2 times 20 feet, which equals 40 feet. Marina gets 40 feet of fencing. This isn't just a number. It directly translates to how much material she needs to buy, highlighting that practical application.
Okay, good. Time for a volume and capacity problem. Problem 5. A water bottle holds 750 milliliters. How many liters is that?
This is a classic metric conversion problem involving capacity. We need to go from milliliters to liters.
Smaller to bigger unit this time.
Right, our conversion factor tells us that 1 liter is 1,000 milliliters. Since we're converting from a smaller unit, milliliters, to a larger unit, liters, we expect the number to get smaller, so we need to divide.
Divide by 1,000.
Exactly. So we take the 750 milliliter and divide it by 1,000. This calculation gives us 0.75 liters. And the answer makes intuitive sense. 750 milliliters is less than a full 1,000 milliliters, so it should be less than a full liter. Specifically, well, 3/4 of a liter. It's a great example of how our understanding of fractions and decimals connects directly to these unit conversions.
Moving to mass and weight. Problem 7. A bag of apples weighs 1.2 kilograms. How many grams is that?
Another straightforward metric conversion, this time going from a larger unit, kilograms, to a smaller one, grams.
So we multiply again.
We do. We recall that 1 kilogram is equal to 1,000 grams. To convert 1.2 kilograms to grams, we multiply by 1,000. So 1.2 times 1,000 equals 1,200 grams. A decent-sized bag of apples.
Oh, yeah.
This problem just reinforces that beautiful simplicity of the metric system's base 10 structure, where conversions are often just a matter of shifting the decimal point.
And finally, a time problem, one we all encounter regularly. Problem 9. A movie starts at 7:45 p.m. and ends at 9:30 p.m. How long is the movie?
This raises that important skill of calculating elapsed time, something we do constantly. The most effective way to solve these, I find, is often by breaking it down into manageable chunks. We start at 7:45 p.m.
Okay.
Let's jump to the next full hour first. From 7:45 p.m. to 8:45 p.m. is exactly 1 hour.
Easy enough. 1 hour down.
Now we just need to figure out the time from 8:45 p.m. to 9:30 p.m.
Right.
From 8:45 p.m. to 9:00 p.m. is 15 minutes.
Right. Quarter of an hour.
And then from 9:40 p.m. to 9:30 p.m. is another 30 minutes.
Okay.
So adding those 2-minute segments together, 15 plus 30 gives us 45 minutes.
Got it.
So the total duration of the movie is 1 hour and 45 minutes long. This strategic approach, breaking it down, it minimizes errors and builds confidence for doing these kinds of calculations in your head.
Now, let's tackle a challenge problem that truly brings multiple concepts together, demonstrating how these seemingly separate ideas interlock in more complex scenarios. This is challenge 1 from our sources. A rectangular swimming pool is 25 meters long, 10 meters wide, and 2 meters deep. We need to find three things: its perimeter, its area, and how many liters of water it holds.
Okay, yeah, this is an excellent multi-step problem. It forces us to carefully select and apply the correct measurement concepts for each part. Let's break it down. First, for part A, the perimeter of the pool's surface. This refers to the distance around the top edge of the pool.
Just the top edge. Okay.
Right. Since the top is a rectangle, we use our perimeter formula, 2 times the sum of the length and width. So we calculate 2 times 25 meters plus 10 meters. That's 2 times 35 meters, which gives us 70 meters.
70 meters, that's the perimeter. Useful if you're putting a fence around it, maybe?
Exactly. Or maybe installing a safety rope around the pool edge.
Okay, part B, the area.
Next, part B, the area of the pool surface. This is the flat space the top of the pool covers, like if you were putting a cover on it.
Right.
Area for a rectangle is length times width. So we multiply 25 meters by 10 meters, which yields 250 square meters. Remember, square meters for area.
250 square meters, got it.
And finally, part C, how many liters of water it holds. This is a two-step process. It involves volume first and then a capacity conversion.
Ah, okay. Volume first.
Right. First, we find the volume of the pool itself, treating it as a rectangular prism. Volume is length times width times depth. So that's 25 meters times 10 meters times 2 meters.
Let's see, 25 times 10 is 250, times 2 is 500.
Right, 500 cubic meters. That's the volume.
Okay, 500 cubic meters, now the capacity conversion.
Exactly. Now for the capacity conversion. Our source tells us a crucial fact. 1 cubic meter holds exactly 1,000 liters of water.
Wow, okay. 1 cubic meter is 1,000 liters.
Yeah, it's a really useful one to know. So to find the total liters the pool holds, we multiply our volume in cubic meters by this conversion factor. That's 500 cubic meters times 1,000 liters per cubic meter, which gives us a massive 500,000 liters of water.
500,000 liters? That's a lot of water.
It really is. This highlights how a conceptual understanding of volume and capacity, combined with just one key conversion, can scale up to incredibly large practical numbers, like, estimating the cost of filling that pool.
Wow, we've genuinely covered a vast landscape in this deep dive, from the precise tiny millimeters to the expansive kilometers, navigating the difference between perimeter and area, distinguishing volume from capacity, dissecting mass and weight, and mastering the fluidity of time. You now have not just the definitions, but hopefully a more robust mental toolkit for understanding and applying these foundational grade 5 measurement concepts, maybe through a slightly more adult lens.
Indeed. What's truly striking here is how these concepts aren't confined to textbooks or, abstract classroom exercises. They are fundamentally woven into the fabric of our daily lives, often operating below our conscious awareness. Knowing these tools empowers you to navigate the world more effectively, whether you're meticulously following a recipe, planning the layout of a room, precisely estimating travel time, or even just deciphering a weather report. It's about translating raw numbers into tangible understanding and confident decision-making.
So what does this all mean for you, our listener? Well, the next time you find yourself grappling with a recipe written in imperial cups and pints, or maybe you hear a scientific report measured in millimeters, or even just wonder how many gallons of gas are left in your tank, you won't just see numbers. You'll have the mental agility, the conceptual understanding, and the practical toolkit to convert, calculate, and truly grasp the meaning and implications of those measurements. You can approach those everyday challenges with a newfound clarity and hopefully confidence.
And my final provocative thought for you to mull on: how many distinct measurements do you actually encounter in a single hour of your day without consciously thinking about them? From the precise weight of your coffee beans, maybe, to the dimensions of your phone screen, the temperature outside, the duration of a conversation, start noticing. Just try to pay attention for an hour. You'll realize the world isn't just communicating in units, it's constantly inviting you to understand its language.
That's a fantastic challenge, a great way to end. Thanks for joining us on this deep dive into the world of measurement. Keep exploring, keep questioning, and we'll catch you next time.